11. I'm going to deliver a tutorial on Bayesian deep learning. And this tutorial is going to consist of two parts. First part, we'll try to implement the stuff that Jaren was talking about yesterday in PyTorch. I will walk you through, hopefully, the implementation. I try to make it easy and understandable. And the second part is concerned with Bayesian deep learning. We will try to take MNIST data set and use several, compare two position functions, random and a smarter one, to see if, it's worth the effort. All right, so I would like to ask you to go to Colab and fetch the latest repository like this. So the thing is that I've noticed that all of you made forks, and unfortunately I had to push some latest updates concerning performance. So if you will be so, I would like to ask you to either update your repository or just follow my instruction on the screen. So anyway, we open this page, see it, all right? And if you just type in mlss-contact and then select master branch, you'll see that there are four. Immediately you'll see the correct notebooks. If you want some challenge or if you want to code something, please select the notebooks that do not have SOLN suffix. If you want just to have a look and maybe if you're not feeling, I don't know, like you want to program stuff, select anything you want. All right, so we take, for example, this notebook, part 1, and open it. As usual, the first step is to make sure that our runtime is GPU, because we'll be doing some stuff for some fitting, and so as not to make us wait for a long time till the process stops. So as you can see, Jaren told you about the possibilities of injecting uncertainty estimation into neural networks, and the way he proposed to do this is via conventionally and very commonly used technique called dropout, together with L2 weight realization, also known as weight decay. So basically, we will be doing this exact same thing. First, let's we'll start by running the first cell. It's service code that will help. That I used to remove all the boring stuff like fit and predict, because these loops, these implementations are extremely common and there is no value in even looking at them. So we first call this, then import NumPy and torch. Hopefully you had, pardon?
Would you like false speaker?
All right, sorry. Certainly.
Thank you.
150. You shouldn't. You don't have to type anything. We don't need to type that URL. So anyway, hopefully you had a look at PyTorch, or you already know what PyTorch is, or you're already a core developer of PyTorch. So hopefully it won't require core developing skills, but maybe I'll explain some basic stuff. Basically, PyTorch is like NumPy with autograd with different argument names. For example, you use D instead of axis, and it also supports a lot of deep learning stuff, optimizers, schedulers, data visualization, and most importantly, constructing neural networks. So while we are importing this boring stuff, just this predict and fit and stuff like that. So what we'll be doing in this part is we'll take a relatively simple function and I'll try to show you how the things are done. Okay, so we just generate some data, and this is our network that we will be using. Yes, all right. So it's a pretty wide one, and it has only 1, 2, like 3 layers. Anyway, for doing this simple task. So, but at the moment this network is deterministic. So if we fit it using L2 visualization and all with only but not dropout, and if we wait for a while, we'll see that it predicts something like this. Check if the plots are visible. You see, well, it does its job reasonably well. However, what can you, as an expert, or what can your user, or what can your client say or infer from this graph about how well this will perform on the text, or how well the network itself knows stuff? Or at least not knows, but how certain it is that its predictions are more or less correct. So in order to make this network capable of estimating uncertainty, Yarin told you that your basic approach is to add stochasticity to weights. However, sometimes it's not so easy to do this, because you need to code, you need to either have some implementation, or if you're not satisfied with the implementation, you need to code some stuff yourself. But the most basic thing that you can do is just add dropout. So that's what he told you about during the lecture, and that's what his research, first research that he did maybe like 3 years ago, that he showed that this is a technique that can be sort of not reduced, but that basically solves a Bayesian inference problem, variation inference problem, and it allows you to just use it for, well, essentially without doing anything. So let's, a reminder that dropout basically gives you a mask, a binary mask, 0 and a special value. In all implementations, the special value is 1 divided by 1 minus the dropout rate. So that in expectation, your dropout yields the same value, the same, not weight, the same vector that it is applied to. Usually dropout is applied to input values that you feed into the layer. So this is basically, now we arrive at our first task. The first task is to, let's say, I hope it won't be a challenge, we'll implement dropout. Of course, there are some already existing functionalities in any deep learning package that you would like to use, but maybe, I just know if you want to test your skills, let's implement it ourselves. Anyway, so hopefully, yes, this has been executed. All right, so here, first of all, there are some comments on how generally you construct networks in PyTorch. Of course, there are much better tutorials regarding the way to work with PyTorch, but at least maybe this will give you an idea. So first exercise is just to sample a binary mask that you apply to your inputs, but binary masks with specific values, with 0 and this 1 divided by, with this fraction, and apply it to your inputs. Let's do it the most crude way possible by sampling uniformly and then checking if everything works. All right, this mask is torch
PyTorch dot, what can we use? We can use any of these functions, rand or rand-like. So I'll use rand-like. Rand returns uniform distribution input, all right? This thing gives you a tensor of uniformly distributed random variables, random variates, that has exactly the same shape and type and device as the input. So then what we do with this mask is we binarize it by doing this step. Self.p is, well, we take only the values that are larger than the dropout rate. Because if we set dropout rate to 0.1, then we want a lot of, then we want a very few number of zeros in our mask. And if we set dropout rate to 0.9, we'll get much more zeros. So basically, that's what we do here. The next step is to multiply this, to apply this mask to your input. All right, so that's what we do. We tell PyTorch to do this, input times mask. However, there's this code won't work right from the get-go because PyTorch is very strict about its data types. So, because mask on this line 15, 15 was binarized, we must actually make it turned into a float number. So that's done using this method .to. Just some simple hack. And this .to usually accepts device data type, or in like maybe some months ago they allowed it to accept another tensor, and it just basically mimics the device and data type of the tensor. So basically they do this. And well, I hope that this would work right from the get-go, but we can't actually test it right now because it's just an implementation. All right, so we have created this layer, and now we'll have to actually somehow use it in our network. So what I propose to you is to copy the structure of the network from a couple of cells above, and just put this new active dropout layer into it. Because this is not very exciting task, I'll just start working as well with you right now. So we just go up, and we can actually copy this, but we need to clean it up. Anyway, we'll take this one and just paste it here. Like this. Now, usually you apply dropout to your inputs. However, there's a special layer in a network, the input layer, which shouldn't be dropped out because you'll be losing the raw information that is needed for feature generation for your actual for your learnability of your network. So what we need to do here is to inject active dropout layer just before the or every linear layer that is not the first one. That's what we do. We take active dropout, sorry, and instantiate it with the rate p, which is provided to us here, like this, and just paste this stuff here. Right, so pretty easy stuff. This way, if you fancy some other neural network in PyTorch, well, it's the most straightforward way of creating stuff. We just run the cell. It finishes without any bugs, without any asserts. And let's build a model and fit it. We fit in the model using mean squared error, like the first one. And we also doing weight decay, so as not to, because this is the thing that is necessary for this technique of making of Bayesification of your networks with dropout. And this function, because we have created this dropout layer that always drops out stuff, we actually need a function that collects the results of forward pass through the whole network. They're random. So we want to collect these passes and stack them in a huge tensor. That thing will allow us, in our later pipeline, to compute the mean, to compute the variance of the network at each point. And this way, you'll be able to actually, well, you'll be able to have crude estimates of your uncertainty, just mean plus and minus standard deviation multiplied by some, but by the value of your choice. People sometimes use 1.96 because normal distribution, but sometimes people just round it up to 2. Anyway. So this function does exactly what I told you about. It, in a loop, this one, it collects the required number of samples and using the function predict, applies the network to the provided data set. Easy peasy. Yeah, there. It finished. I hope that you all got the same task bar, progress bar. Anyway. Yes? Mm-hmm. True. When in the Bayesian version of the network, you do stochastic forward passes all the time. In typical application of dropout, typically dropout works depending on the regime that you set. In PyTorch and in models that are created in Torch, there are two regimes, train and evaluation. I think it is pretty obvious that in evaluation you turn off the dropout. But here, because we want to have a probabilistic judgment, probabilistic inference, we want to know the distribution of the outputs, we latch the dropout to always be active on any pass, even when you type model.eval in your code. But if you have a look at the internal code of the library that we are importing, this one, MLSS 2019, there you'll see that during train it uses model.train, and during eval, during predict, it uses model.eval, which is a correct and, let's say, documented way of doing this. So, unfortunately, if I use just Torch, Torch, of course, has the dropout layer. You don't need to redo stuff. Unfortunately, the stock layer, by default, has deterministic pass on eval and stochastic pass on train. There's another layer that also behaves differently depending on your regime, and this is batch normalization. During train, it accumulates the statistics and stuff. During eval, it uses accumulated statistics. So in order not to semantically, let's say, change the meaning of the word of the two regimes, we had to implement a dropout layer called active dropout that always drops out. So this is the bit of code that we had to do, the first bit of code. Let's delete this cell because it's just empty and run the result. If we were just doing if you just doing deterministic forward passes, you would get this picture. The deterministic pass, actually, you recall it has been already run. It drew a blue line that went perfectly through the large circles. We don't want to do that. We want to sometimes compute variance. We want to compute maybe entropy if we know if we have some assumption regarding the distribution. Yes, please. No. This is just, I multiplied, yes, this is, I just multiplied it by 2 and made it like this. It has no, we don't know the distribution, so it may be very biased, it may be even skewed, we're not sure. That's why we always keep some data set for validation, where we actually tune our parameters. I'm not sure about confidence bands because, we tune dropout, we tune weight decay in order to actually improve the probabilistic performance of our network through maximum likelihood of the posterior distribution that actually rises in this network. Improve its performance on validation and by selecting the proper dropout rate, proper weight decay. Now, sometimes, this is the second piece of code that we'll have to implement in this part. Sometimes, we don't just need a simple stochastic forward pass. There are many reasons for this. One of them is, for example, you are trying to do some optimization and you have some unknown surface which you want to find some optimal point that you wish. However, if you just take the code that we have written and apply it there, you'll come into the following problem. You take 2 adjacent points, but then you see that they are uncorrelated, independent, sorry. And here's why. Each time the stochastic forward pass in this current version does its job, it draws an independent realization of a Bernoulli mask. And in this particular example where we want to optimize function or even compute some integral value of along its paths, we don't do this. We don't need this breaking of, let's say, dependence between the adjacent points. So what we need to do is to find a way to somehow freeze the mask, use the same mask on every data point that we want, and then rinse and repeat. Freeze another mask, draw it randomly, of course, freeze it, apply it to all the data points that we are interested in, unfreeze, then freeze again, stuff like this. So this, just from out of the box, no package supports it, aside from special ones. TensorFlow probability does this, but in PyTorch, but there is like, but I think it might be interesting, useful to try to see how different approaches of implementing stuff can help you in your, for example, work, because sometimes you need some extra enhancement, extra feature that is not available in a certain package. So, as you can see, if we plot the sample, if we take each point that we sampled, and if we take the result of that we sampled and plot it along the whole, plot it along the whole X domain, we'll see that they're very noisy. You see, like this blue line behaves. It won't give you good estimates of integral measures, or you won't see where the minimum is because right over there you see like there is right close to the 0 point on X. There might be some noise that will move you somewhere. So what we have to do is, unfortunately, we'll have to implement this and ourselves. So let's scroll to this cell. I gave it a thought. I thought for a while how this should be, let's say, how this idea should be conveyed to you of freezing the weights. And I decided that this simple approach of making a so-called trait class that bestows freezability on weights would actually be more intuitively understandable. Although it is not the best solution, there might be better ones. I think at least it gives you the idea of what we want our dropout layer that we are going to implement next, of what we want it to do. So first of all, we initialize, and but by default we initialize to unfrozen weights. The second line, the second method, unfreeze, basically does the unfreezing. The third method allows us to check whether we can access a frozen mask or weight or whatever. And the last line is a virtual method, which we'll have to re-implement in our merged dropout linear layer. Now, of course, having defined a base class, we need to actually create some levers. There's a difference. Okay, so some switches that we can use and instruct our network to either freeze or unfreeze. Since we want to create arbitrary networks, and in the next part we'll be doing some convolutional stuff, we just write a simple loop over the structural components of your network through this model.modules. Basically, it gives you all the structural components of your model and in the depth-first manner. So basically, just so if you have some shared weights, it will not cause you any problems. So this is what these two functions do. And here is a task for you, but if you want, but I'll still be live coding so that you can follow me, and I will explain stuff. We shall use freeze and unfreeze to create a function sampler. The result of the application of this function, of this procedure, we expect it to give us evaluations of the network, but evaluation of the network that do not break the dependence between the adjacent points. You can basically, the exercise is here, but just to reiterate, you can take the function point estimate, which was above, I mean like in the notebook, and you basically need to inject 2 lines into that function in order to create a function sampler. So I'll just go scroll up and copy that. Here, this function, I copy it, and there we go. Strange. This is not the function we're looking for. Yeah, this one. All right, and let's remove the last line because it's useless. Below, by the way, you can see that the functions that we'll be creating as a result of adding these 2 lines conceptually changes the result. So as you can see, if you scroll up a little bit, you'll see that freeze function instructs each layer to freeze itself, freeze the mask, and basically returns you the model. So we just take this freeze and we do this. It's not very, let's say, clear, but we can always compose functions. So this thing, the line 11, it just applies predict to a frozen model on a specified data set and stores it in a list. All right? Basically, we're done. Because when we will implement the freeze operator on our layer, we will just make it so that when the operator is called, it always samples a new mask or a new weight. So we won't have to actually explicitly unfreeze stuff. However, since we are changing the sort of internal regime of the network, and later we might be interested in reusing the stochastic passes, in the end, it's a good practice to return the network in some known regime. So basically, I think that it would be useful just to unfreeze the network over here, model. That way, we know that after the application of this function, our network sort of is in a known state, right? And there we go. Just simple copy-pasting. Yet another exercise is to actually marry the dropout layer, the active dropout layer, with the linear layer. There's a lot of formulas here. Anyway, so the first formula with I can't identify it. Okay, the first formula over here is the application of dropout to the input. The second formula here is the application of a linear layer to the input, to the intermediate result of the last operation. And basically, we will do both. We will implement these two things. But this time, we won't draw our mask using uniform or torch Bernoulli or something. We'll just use the out-of-the-box function that does dropout for you. This function is f.dropout. This dropout performs exactly the first expression over here with the distribution of the mask defined over here. So, okay, let's start coding. We take, suppose we have no frozen weights, okay? So we do this. X tilde is f.dropout input. His reference input, then we have to put the rate, self.p. We expect that our layer will have this attribute. And we set it to true, because the last argument actually controls that. Okay, we also have f.linear, which under the hood does all, just calls matrix multiply, and actually sees if you pass a bias parameter to it. Anyway, it applies a linear, or also known as more correctly called affine transformation to the input. Let's write it. Return f.linear. Well, we should put the input here, x tilde. Yep. Then we'll call our weight, because we know that at this moment our layer will be operating in a stochastic path regime. And we have already implemented stochasticity via this dropout thing. So self.weight, our parameter that we are learning. This is the parameter that under the hood, the network gives to the optimizer, ADAM or ADAMAX or RMSProp or SGD. So, and we also add the bias, because why not? We shouldn't forget it. Self.bias. Now, we have implemented the stochastic forward pass, which knows nothing about the frozen weights. But we should, if the weights, some weights are frozen, we should actually condition on this knowledge and use just the linear layer, just the linear function, because in the following, we will take the mask of the Bernoulli of the dropout and apply it not to the inputs, but we will sort of apply it to the weights that will result in exactly the same outcome as if we were just applying to the inputs. So we just write if self is frozen, then just return. Maybe like, where's the twist check here? Anyway, f linear and x tilde. Oh, no, this is wrong. We don't have x tilde yet. We have only input here because this is the frozen deterministic forward pass. Input, self. And let's have a look at the terrible design choice that was made a little bit above. Cool. Dope. And the terrible design choice was that we actually named the storage of our future sampled weight frozen weight. Okay, since we need to make this work, let's just paste it here. All right, so I hope it's clear that if we are frozen, then we apply a linear transformation using the frozen weights. If we are not frozen, then we apply dropout and apply the linear transformation to the result. Now, we need to thinking about how the combined operations work. We actually can transfer the effect of the mask onto the weights away from the inputs. Here's how we do. This is a lot of this is a maybe it's a little bit intimidating, this notation of what's this notation? It's like some arc. Anyway, so we take the mask of the input, of the ith feature of the input, and apply it basically to the column of our weight. This way, this function is, I have implemented it for you because I know that all the exercises up to now were somewhat boring. So here, in this function, it does exactly what is written above it in the equations. First, we disable the autogradients because they give you a huge speed up. You don't need to backpropagate through the frozen weight because you are working in an because you expect to be working not while training, but while actually predicting stuff. So we don't pass the gradients here. Maybe it is entirely possible that within your train loop, you might want to actually adjust the weight that you have sampled because you, or maybe you compute even your loss on the whole, or not on point estimates, but on the functional realizations. So this line, number 7, it is needed in our, well, it is how to say it? It's all right if we leave it here in the current tutorial, but depending on your problem, on the task that you're trying to solve, this line might not be needed to you. Anyway, first we sample, we create a tensor of probabilities that actually is a row vector. And this row vector later will be populated with Bernoulli random variables on line 9. And then we just multiply stuff and store our result as a frozen weight variable. Now, a small comment. If you want to implement some additional working stuff in PyTorch in a module, you can't just, for example, put you do some multiplication and you just store it as an attribute, self.cache, for example. Self.cache is equal to some cached value. This way, unfortunately, in some instances, you will get unexpected errors that are due to this cached value being misplaced on not the device you want when you transfer a model. So the correct way of registering cached values in Torch networks is through register buffer. So this is I just recited some portion of documentation to you. Anyway, we run this stuff, and it works, and then we just assemble the layer. This. Oh, I forgot to run this thing. Just usually the implementation of methods of a class in Python is placed in the class declaration itself. However, it is perfectly possible to do it like this, although in your production code, I would discourage you from doing this. Just for illustrative purposes and for structuring of the narrative of the tutorial. And here, again, another boring coding exercise. Let's just take the module constructor that we created a while ago, and just copy it here, and instead of active dropout, let's put dropout linear. Since we and instead, not only active dropout, we also drop out linear layers themselves, because we designed the class in such a way as to be compatible with linear layer. Okay, let's do this. Let's copy from here. Where is it? Not here. There. Let's take this code, this very sophisticated neural network, and put it here. Where? There. All right. Copy and paste. All right. Since we implemented a fused layer of dropout and linear, we just take this. Add the parameter p is equal to p. That will be funnier. Here the same stuff. And we do not drop out the first layer, just remember. There. And now let's fit and see if we got, if our efforts were worth it. All right. So, well, it seems to have computed something. And what do we have here? I hope that well, it looks nice. You see, the orange noise is noise. But the blue lines, they are actual smooth, not smooth, but actual continuous curves. Because you see, our network is a linear transformation, leaky ReLU. Linear transformation, leaky ReLU. It should be continuous as a composition of continuous functions. So basically, we did what we were supposed to do and made it possible to sample the functional realizations. Now you can see that sometimes there is a simple solution and there is a harder solution, but they give you different benefits. Point estimate function is easy to code, just plug in, use Keras, use, I don't know, Lasagne, if you still use it. Anyway, you can just plug in dropout there and it works. You forgo the dependency between adjacent points and you won't get functional estimates. In order to make it work, you'll have to, unfortunately, put some effort. by the way, this tutorial, again, I reiterate that it is not the solution to this, let's say, functionality, but you can, I hope that you will be able to copy stuff from here and put it in your work code and see that it won't take you a lot of time of re-implementing this. By the way, well, no, by the way. It was shown that Yarin explained in his lecture that altogether this mixture of dropout and weight decay gives you actually the Bayesian network with some pretty complicated point mass distribution. This one, sorry, this one. But in some sense, it can be regarded. In some sense, I mean that together with weight decay, it approximates the following evidence lower bound. Well, I normalized it by the number of samples in the train set. And the key here is that the weight decay should, first of all, you can see that it depends on the probability of dropout. So if you drop everything out, then you need to put weight decay to 0 because basically the network is just nothing. It always drops off stuff, so it computes nothing. But the most important observation from this tiny expression is that the more data you have, this is especially relevant in Bayesian active learning, which is the next part of the tutorial, is that you must decrease your weight decay the more data you acquire. So these questions are, as it's written, if you are interested, if you fancy doing some stuff, you can just try to code and to replicate the results and see how differently the parameters make the function samples look. The solution is given in the supplementary notebook, which has -soln in its name. And next thing, before we move on to part 2, is it's also optional. It's what to do with convolutions. Basically, in convolutions, the main difference is the behavior of dropout. You do not simply drop out your pixels in an image or the spatial features on the tensor in some intermediate layer. You take this four-dimensional tensor, batch, yes, just consider a batch of 1. You take this three-dimensional tensor, you have space here, pixels, and you have features over here. And in dropout for image data, you drop out entire features. If your mask tells you to drop out something, you drop out all pixels that are in that feature slice. That's the main difference. And effectively, it changes nothing in the code that I provided above, except one thing. In PyTorch, in order to invoke a convolution, you have to pass a huge number of parameters to it. So I implemented this layer for you and put it in the hood, under the hood of the library that we installed at the beginning. And the final thing is, if you want, after the school finishes, if you want to revisit this stuff and maybe refresh, the last part of this part, the last section of this part, is a reminder on stuff that maybe some useful stuff on what is being usually done in variational inference. Okay, now let's move to the second part. I have already preloaded it, so it should work. This part isn't that heavy and boring in terms of coding, but still there are two tasks that we'll have to cover, three tasks that we'll have to cover. First of all, just let's run all the notebook until, please, these service messages are very useful. So we wait for a while, okay? Then again, we import torch and fit predict. And here I just copied the function from the previous part and just pasted it here and renamed its arguments. It used to be n samples instead of n draws, and that's it. I also declare a function that samples the output of the network and applies softmax to the output, so that in the end, using this function, we can get a sample of probability distributions. Because we will be doing MNIST, yes, we will actually have a categorical distribution. Oh, sorry. As an output of the network itself, we'll have some raw so-called logit scores. But when we will be doing entropy estimation, we will be doing prediction, we will be using the values of probabilities themselves. So basically, this function does this. This function computes the mean probability distribution along all by just averaging through the random functional draws of the function above. That one was called sample proba. Next, we move on to predict label, just maximum posterior class label, nothing fancy here. Evaluate, basically it uses the so-called confusion matrix, which is basically a matrix that on its rows, it lists the predictions, yes, and on its columns, it lists the ground truth values, and basically gives you the frequencies of what value was predicted or mispredicted. Very useful matrix. And this is some service function that will hopefully provide pretty plots to us. All right, so to recap, Bayesian active learning, or any active learning for that matter, you need three blocks. The model, which can, let's say, understand data, and fit to it. You need a so-called acquisition function, which takes a model and a data set and gives out to you some set of observations that it thinks are most useful for the model. And it has the most important stuff is the so-called oracle, but in human language, it is an expert. The person or this another machine learning model that provides labels for the samples, for the instances that you want to acquire for your model. We will move to this hopefully in 5 minutes, but to jump ahead a little bit, we will actually see, we will take each example in a data set called pool. We will take each example in the pool without looking at the targets. No. We are not allowed to look at the targets. We take each example and we measure the mutual entropy of this example's supposed target with the weights of our neural network. And we do this by through Monte Carlo estimation, averaging, stuff like this. So basically, we will try to make some informed choice. Of course, you cannot use, I reiterate, we cannot use labels because that will be cheating. Okay, so the model. first part, we create a simple module which uses two convolutions, convolution with dropout, which I implemented for you, and a couple of linear dense layers. And then in the forward, in every time you want to implement in PyTorch some custom module that does some fancy stuff, you will probably need to declare a class and define a forward method, which takes in inputs as a tensor. It may take even keyword arguments. It can take even several tensors. So you define this method and basically just apply the blocks that you constructed in dunder init. You apply it to the input and get the output. So, the acquisition function. Now, there are many acquisition functions, but we will first use random acquisition. It is the most uninformed, it is really simple, and actually sometimes quite hard benchmark to beat. Here is how it looks like. First, on the first line, I fix the randomness to some number, to some seed. And then I define the acquisition, which takes dataset, model, the number of points to request, and the number of draws of random replays to make. And then within it, it just takes it just randomly picks out a certain number of data points from the data set that I provide. This is how random acquisition would work in general. Now, I have 30 minutes. This thing, I haven't, where is it? I seem to have skipped a very important function. Oh, no, I just, my predict, anyway, never mind. So this here is a function that downloads the MNIST dataset and constructs the training dataset, initial training dataset, the dataset from which we will be acquiring stuff, of course the validation set, and it also gives you the test set. And well, when designing the tutorial, I made it so that it is possible to switch to the MNIST dataset similar to MNIST, which features characters from Japanese alphabet. I guess it's called kanji. And of course, it works a little bit on this dataset. It works. This system, the code works a little bit in terms of performance. The final performance first works a little bit worse. So we run this cell, and it well dumps a lot of text into our into the output. Basically, it's just downloaded stuff and prepared the data sets. And also, we need an oracle, and the oracle is defined by this import from the libraries that I prepared. Basically, this thing just takes the data set and the indices that we wish to acquire, and it just takes these elements from the data set and returns it to you. So we just import this, and let's run the active. Let's create the final element we need to do. This is like which joins all the building blocks that we've discussed, is the loop itself. Basically, the active learner loop is a simple thing: feed and acquire. Feed, acquire, feed, acquire. First we feed, then we evaluate the stuff that we're interested in. And we also pay great amount of attention to satisfying budget constraints, because in typical applications of machine learning, you cannot do active learning without considering finance. For example, it might be very costly to obtain a label for an MNIST digit. Anyway, and eventually the loop stops. Okay, so this function is unfortunately pretty long. I focused on the core of the loop. The line 23, feed the model. Line 27 through 34, we collect the statistics because I want to illustrate stuff. And the rest is just this acquire, collect steps. All right? So first we run the baseline. Oh, yeah. This piece of computation might take about 5 minutes, hopefully, and start. It should start actually outputting some stuff right now. Am I using GPU? Let's have a look. Runtime, change runtime type. Oh, of course I'm not using GPU. Thankfully, we can restart runtime, use GPU. Yep. It would have taken prohibitively long time running it on CPU because convolutions on CPU are much slower. Anyway, so let's run, let's restart. Yes. And let's run all before. You don't need to do this because you have actually selected the correct runtime. So we wait for a while, a little bit until it finishes. All right, cool. Now we run it. Hopefully it will start outputting some images right away. But it still takes, oh, all right, look, we have, it's alive. I have instructed the active learning loop to request batches of 3 images from the pool. And as you can see, it seems to be doing something. It outputs, yep. I need to zoom out a little bit so that you'll see that it, yes, hopefully. So basically, right now, it uses 48 observations. It has acquired all 48 observations altogether out of the budget of 150. And it uses a random acquisition function. And, well, it should be like, in the end, it should have 5 rows of digits. While it is working, I think it would be smart if we jumped a little bit ahead and started implementing Bayesian acquisition function, the acquisition function based on mutual information. Because why not do some things? You know, watching the kettle boil won't speed the process. So let's skip ahead a little bit to here, and here we need to implement this acquisition function. Now, this acquisition function takes, well, in the most general way, it takes in a model and takes in some data set of points, small subset of points, yes? And it judges whether this subset of points is valuable. Now, the naive, this is called naive belt. Naive Bayesian acquisition through disagreement is it just sums over all the data points that were given to it. And this actually allows a really simple estimate of usefulness. We can just take the mutual information on every data point in our pool, order the values in decreasing order, and take the top how much n request values. Let's do this. Suppose we have a function called mutual information. Mi is equal to mutual formation. Begin with this. Proba. All right. Next thing, we should sort it. Okay. Order is mi dot argsort. I hope that you see the similarities. In NumPy, we also have argsort. Now, mutual information here would return a flat array of values, one per each element in the data set. So we don't have to specify any excess of sorting. But we should specify, and this is the key difference between from NumPy. In NumPy, you don't have the argument of descending order. You just have to flip the array. The funny thing is, PyTorch has some troubles in flipping the array using the pattern like you put double colon and then -1. It seems to have some trouble with it. Anyway, so we explicitly write descending is true, and finally this gives us the order of the mutual information values in descending order, yes, and we'll take just the the top values there. Return order and request. All right, seems to be all right. Let's run this, and it hasn't finished. This means that we're still producing some digits. Okay, it should take the last step. We've spent some quality time coding, and there we go. Let's inspect the results first. Well, we'll compute accuracy using the confusion matrix and plot the accuracy. You see, well, it had nowhere to go but up, okay, because we increased the data set and we actually we use like 200 epochs on each feed, so it should go up. We should learn. But let's also have a look at what was acquired by this random acquisition function. In the pool that we prepared, it just happened to be that there are much more zeros than everything else. This is unfortunately typically in any real data set that you deal with, there are a lot of junk and there are a lot of useful stuff. Here, there are a lot of zeros which random acquisition just blindly acquired and used to train the model. Hopefully that with a smarter mutual information criterion, we can do better. All right, so this Beld acquisition seems to have been completed. Let's check if the API coincides with this one. Yeah, it seems that we need to do also this thing, just so that everything is in correct data type. Okay, so we copy it here and do it like this. All right. Now, next thing is we need to implement entropy. Of course, the best way, if you do not implement stuff yourself, if you reuse someone else's stuff. Preferably someone else's who actually knows what they are doing. So please don't use my stuff. I don't know what I'm doing. Anyway, here, this is, I warn you, what I'm about to do is not how you implement this, because you should always pay attention to, when working with float numbers, float 32 especially, you should always pay attention to near zero values or occasional not numbers. So what I'm about to do is a typical implementation, but in PyTorch there is a better way. Anyway, so for a categorical entropy, we need to take a logarithm of the probability and multiply the probability by this logarithm and sum this and then flip the sign. Well, in calculus, 0 times logarithm of 0, well, basically it's undefined, but if the term before, if p dot times log p and use the same value, and in the limit it is a really well-defined number called well-defined 0. So here, if you will be coding it in C, for example, you have to explicitly check for zeros. Anyway, what we'll do here is some trick like this. Return minus torch dot sum, and we are instructed by the docstring and the comment to use last dimension. Okay, we shall do this, -1. And what should we put here? Let's put a very useful word here, values. Okay. This is not a very good name, but anyway. So here we take proba times torch dot log proba. Oh, it encourages me, you see? 1 minus, and now here is a dirty trick. We add a tiny number here. We are guaranteed that the probability is non-zero. We can always clip it from minus stuff to plus stuff. But you see, like this 10 to the minus 12 is a really small number, and it won't fit into a float value. But if we have 0, explicit 0, or very, 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 like really underflown value in proba here, it will dominate. But then, after being multiplied, after being taken logarithm of and multiplied, it will be still a very small value. So we're sort of working here, we're sort of safe here. And yeah, you see? I have declared the function correctly. It doesn't, the syntax is correct. Okay, now mutual information. The mutual information has a neat formula which I put, where is it? Yes, here. First we compute the average predictive probability, posterior predictive probability of each class. Then we compute each predicted entropy and average it. And finally, we subtract one value from another. That is what this formula says, and it is quite simple to implement. Let's call it entropy expected. Okay. What? We'll be using this function, categorical entropy. Okay. Categorical entropy of something. And the next one would be expected entropy. Yes. Which is also categorical entropy of something. But the first line, number 5, actually, uses the averaged probability. So we write proba dot mean, just like in NumPy, except for this part. Dim is 0. I don't know why, no, I actually do know why. it's historical reason they use dim, and right now just asking to redo the whole infrastructure just for one parameter is silly, so we'll have to stick with dim. Okay, the first line, number 5 actually, does what it's instructed to do. Categorical entropy of the average distribution. Now the second line is, it should be the expected entropy. So we take proba. The definition of expected entropy computes the entropy with respect to the last dimension of the tensor proba. And now we need to average it. Dot mean dim is 0. I especially like that these lines align quite nicely with each other. And return the difference as instructed in this formula. Expected entropy, minus entropy, entropy expected minus expected entropy. Entropy, all right. No syntax errors, good. Well, now we're ready to use a smarter acquisition function. And hopefully it won't swear at us. Why does this keep on showing up? See? The experiments are, well, I designed so that they use the same initial conditions, except for randomness of drawing the masks and initialization of the network parameters. Oh, bugs. What happened here? I actually did not need to convert this into NumPy because everything is in the PyTorch domain. You see, this is why sometimes live coding fails, because you might forget something and you see, like, you get embarrassed. Anyway, so the problem here was that that .argsort returns a torch tensor, and I forgot about it. I thought it was returning NumPy tensor because I was actually explaining that the similarities between torch and NumPy. It's explainable but unforgivable. Okay, so implemented entropy. All right, it has been implemented. Mutual information, cool. And let's rerun this. This time, I think it won't raise any exceptions. Well, it seems to be working. This takes slower, more time, a little bit like more, like 2 seconds more, just because it has to compute the entropy and this extra step, because the random acquisition function just samples some indices and threw them back at you. Now, here, basically this is the last exercise that I wanted to do with you during the tutorial. And while it is brewing, while it is boiling this kettle of a neural network, I'll just explain to you what you should expect from the rest of this notebook. Well, I provided some questions for you if you want to have some homework. It won't be checked. So try k-means data and probably attempt at replicating the figure that I have linked to in this paper. But this time you should, but make sure that you run your experiment several times, store the data, and then take the mean and plot not standard deviation confidence bands, but interquartile confidence bands, basically 25% quantile and 75% quantile. Now, next thing is if you try to increase the number of requested points from 3 to some reasonable number, like you have to, you take 3 points from the pool and then you rerun the whole process spending money on electricity and stuff like this. This is pretty wasteful. So your natural, the first thing, knee-jerk reaction would be to increase the number of elements that you request from the pool to make things faster. Unfortunately, the belt criterion that we have just implemented and that is currently boiling, it was designed for single point acquisition, and that we are using, and the fact that we're using 3 points, we're actually stretching it a bit. Now, recently there came out a paper which improved belt acquisition criterion so that it works naturally with batches. Unfortunately, the main problem here is twofold. First problem, well, it works fine and it's theoretically sound. It is computationally expensive to go through the subsets of size 10 from your pool, because that's combinatorially many elements you have to select. So you'll have to approximate here. Random search, greedy optimization, stuff like this. Secondly, this also comes from the fact that even for as data of a batch, requested batch of size 10, which is small, but the reasonable sizes will be much bigger, but you have to compute entropy. The first term in the mutual information criterion that we are using here is entropy of expected predictive distribution. And this entropy will feature sum over a very large sum over all the labels, all combinations of the labels of the elements in your data, in your small 10th sample batch. So this is also the second problem. If you follow the link, I forgot to scroll down, sorry. If you follow the link, this one, the authors will provide you another link to a GitHub, and that GitHub is really, it's well written, but it's hard to understand. The author implemented out of, let's say, memory computation with, let's say, continuation of this entropy because of just the fact that you need a large sum over all elements. But it works. And second thing is a more classical thing, is as a homework, you might try to correct the uncertainty estimate, by which I mean that if you take an average probability and you plug it into this sum of logarithms, of products of logarithms, this will actually be a biased estimate because of the logarithms, especially. And there's a classical technique known from the dark ages, not the dark ages, but from the 80s, 70s, jackknife correction. Basically, it allows you to take your estimator and take your data. And if implemented correctly and with some thought, it can, in linear time, provide you with a reasonably well working correction to your biased estimate. The idea is very simple. You apply leave one out estimation. You knock one data point out, you compute your estimator. You knock another data point out, you compute your estimator. Collecting all these values of your estimator, you take their average value and subtract it from the estimator on the whole data set. Scale it up to the number of the elements in the data set -1, and there you have it. This is the bias correction that will solve this problem. And the thing is, if you use biased estimates in your acquisition function, you're maximizing it. So what are you maximizing if the value that you're maximizing is biased? You're not sure. So it is really, it might be worth trying to work this thing through and see if it gives any better performance. Now, let's see if we've boiled this water. Yes. We'll have to wait 10 seconds and plot some small plots and a tiny little comment on the plots. And it is complete. Okay, so let's compare the results of random acquisition with a smarter one. All right, accuracy score in this particular run is higher than for belt than for random. Okay, seems to be doing this job well. Okay. Of course, when we want to publish a paper, we need to rerun these stochastic experiments many, many times so that we'll get reliable estimates of the performance. Now, the next thing is a very interesting one. Let's have a look at the number of classes the system requested. You see, in the first picture, we had very many zeros requested by the end. Here, it actually shows us the harder examples that our neural network has to deal with. You see, unfortunately, there's a lot of colors here, but the projector seems to be doing this job well in terms of color reproduction. So the blue one, 0, seems to be growing along with the olive one, 8. You see, if you plot a lot of digits from NIST, you'll see that people draw their 8s any way they want. Even an 8 can look like a 1 because the loops in each side can be just so squeezed to make it look into a 1. Or they may be very fat. You see, the most simple digit of NIST turns out to be 1. You see, by the end of the run, it requested 6 elements in total. The next simpler digit is 7. It's the gray line over here. There's just above the, what's supposed to be orange here. So because 7 is just like a corner, it works. And basically, that is all. And we can have a look at the final acquired sample. It doesn't give you stellar performance in terms of validation set, only 86%, and the current state of the art on MNIST, which is very important, is 99 point something, 0.5 or 6, I don't know. So yeah, that's it. It seems that a smarter way of approaching Bayesian, of active learning, yields some interesting results and costs not that much. That is all.